Two-governor limit errors account for the vast majority of Salesforce production incidents. Not rare edge cases, the same too, in org after org. The SOQL 101 error and the CPU time limit. Both are completely preventable. By the end of this tutorial, you'll know exactly what triggers each one, how to read your debug logs to spot them early, and the specific code patterns that make them impossible to hit at any scale. Salesforce runs as a multi-tenant platform, meaning thousands of companies share the same infrastructure. If one Apex transaction could consume unlimited database queries or processing time, it would degrade performance for everyone else on that server. Governor limits are Salesforce's way of enforcing fairness. They're not arbitrary restrictions. They're the contract that keeps the platform reliable. Understanding that framing changes how you think about working within them. The tricky thing about governor limits is that they almost never surface in development. You write a trigger, test it on a handful of records in Sandbox, everything passes. Then it goes to production, someone runs a data import with 200 records, and it crashes. The limit was always there. Your test data was just too small to hit it. This is why bulkification isn't optional. You have to write code that handles one record and 200 records identically. Every synchronous Apex transaction gets exactly 100 SOQL queries. That's the total across your entire transaction. Triggers, helper classes, flow-invoked Apex, everything. The moment your code issues the 101st query, Salesforce throws a system.limit exception with the message, too many SOQL queries, 101. You cannot catch this exception with a try-catch block. The entire transaction rolls back. No partial saves, no recovery, everything undone. The N+1 query problem is the root cause of almost every SOQL 101 error. Here's what it looks like. You have a trigger on account, and inside the loop over trigger.new you write a SOQL query to get related contacts. That feels natural. You're processing one account. You need its contacts. But if the trigger fires on 200 records, you've just written 200 queries. One per record, plus any queries that ran before the loop. You hit 101 before you're halfway through the batch. When the 101st query executes, Apex throws the exception and you see it in logs and in the error returned to the user. The message is always identical. System.limit exception. Too many SOQL queries. 101. What's useful about this error is the stack trace. It tells you the exact class and line number where that final query ran. That's your starting point for the fix. The error is telling you precisely where to look. Open setup, go to debug logs, and add a trace flag for your user at finest level. Reproduce the error, save a record, run the operation that's failing. Then open the log and search for limit_usage_for_NAS. At the end of every transaction, Salesforce writes a section showing every governor limit consumed. How many SOQL queries ran? How many rows were returned? CPU time used? DML statements? All of it. The line just before the limit exception in the stack trace shows you exactly which query was the 101st. The fix for the SOQL 101 error follows a three-step pattern. First, collect all the IDs you need before you loop. Second, run one single SOQL query outside the loop using an ION clause. This fetches all the related records at once. Third, store the results in a map keyed by the ID you'll use for lookup. The syntax looks like this. You create a map ID, list, contact, loop over the query results, and group them by account ID. Now you have everything you need, indexed for fast access, using exactly one SOQL query. Inside the loop, instead of running a query, you do a map lookup. The syntax is contacts by account ID.get, acc.id, that returns the list of contacts for that account instantly, from memory, with no database call. This is called O1 lookup, constant time regardless of how many entries are in the map. Whether your trigger fires on one record or 200, the total SOQL count stays at 1. That's bulkification. The pattern scales because the number of queries doesn't grow with the number of records. Sometimes the same query result is needed in multiple methods during the same transaction. Maybe your trigger calls 3 different helper classes, and each one needs account data. Without caching, each call issues its own query. With static variable caching, you query once and share the result. A static variable in Apex is initialized once per transaction and persists across all method calls within that transaction. You check if the variable is null. If it is, run the query and assign it. If it's already populated, return it directly. Every caller gets the same map without issuing a new query. The CPU time limit is 10,000 milliseconds for synchronous Apex, 10 seconds, and 60,000 milliseconds for asynchronous contexts like queuable, batch, and scheduled Apex. Here's the critical detail. Salesforce does not count SOQL query time or callout time against your CPU budget. Only your code's actual execution time counts. That means loops, string operations, sorting, JSON parsing, and any computation you write. A transaction that runs 90 SOQL queries but does heavy string work in a loop can still hit the CPU limit while staying well under the SOQL limit. The most common CPU time killers are things that look innocent in isolation but compound inside a loop. String concatenation using plus equals inside a loop is one of the worst. Each concatenation creates a new string object in memory. The right pattern is to build a list, string, and call string.join once at the end. Sorting large lists, especially with a custom comparator, is expensive. JSON.serialize on large object graphs takes time. And recomputing the same value, like a formatted label or a tax rate lookup, on every iteration of a loop that runs 200 times multiplies a small cost into a large one. System limits.get CPU time returns the number of milliseconds your code has consumed so far in the current transaction. You can call this at any point during execution. The pattern is to define two thresholds, say 7,000 milliseconds as a warning level and 9,000 milliseconds as a bail level, and check at the start of each loop iteration. If you're past the bail threshold, stop processing the current record, add it to a deferred list, and skip to the next. At the end of the method, enqueue the deferred records as a queuable job for async processing. When you detect that a transaction is approaching the CPU limit, the cleanest solution is to enqueue the remaining work. The queuable interface lets you run Apex outside the current transaction with a fresh set of governor limits. Your trigger or controller stays well within the 10,000 millisecond sync budget because it detects the CPU pressure early, hands off to a queuable, and returns immediately. The queuable executes separately and gets the full 60,000 milliseconds async CPU budget, 6 times more than the sync limit. The syntax is system.enqueueJob, new your queuable job, deferred records. One of the most expensive patterns in Apex is calling a method that builds a large data structure inside a loop without caching the result. Think of a method that queries all tax rates, builds a map, and returns it. If you call that from inside a loop processing 200 orders, it runs 200 times, rebuilds the map 200 times, and issues 200 queries. The fix is a static variable. Before you call the method, check if the cached variable is already populated. If it is, return it immediately. If not, build it once and store it. Now that expensive work runs exactly once, no matter how many times the method is called in the same transaction. When you need to process tens of thousands of records, far beyond what a single trigger or queuable can handle, Batch Apex is the right tool. You implement database, batchable, define a query in the start method, and Salesforce splits the results into chunks, 200 records per execute call by default. Each chunk gets its own complete set of governor limits. So a batch processing 10,000 accounts runs 50 separate execute calls, each with 100 SOQL queries, 10,000 milliseconds CPU, and 150 DML statements available. The total work is unbounded. Each chunk is bounded. Start your audit by searching every trigger file for a SOQL query inside a for loop. The pattern to grep for is select appearing inside a for block. If you find one, apply the collect query map pattern. Extract the IDs before the loop, run one query with IN, ID set, and build a map from the results. This is the single highest leverage change you can make to an Apex codebase. Most SOQL 101 errors in production are caused by exactly this, and one refactor per trigger eliminates it permanently. After every non-trivial Apex change, run it against a realistic data volume in Sandbox and read the debug log. Search for cumulative_limit_usage. Look at the numbers. If a transaction is using 8 of 100 SOQL queries, but 4,000 of 10,000 milliseconds CPU on a 50-record dataset, it will likely hit the CPU limit on a 200-record dataset. The log tells you this before you ship. Reading cumulative_limit_usage should be part of every code review. It takes 30 seconds and shows you exactly where a transaction is trending. The pattern that combines everything in this tutorial is collect IDs before looping, run one query outside the loop, index results in a map, cache expensive values in static variables, check system, limits.get CPU time, at a defined threshold, and enqueue any deferred work as a queuable. Applied consistently, these patterns make it structurally impossible to hit the SOQL 101 error and dramatically reduce the risk of CPU limit violations, regardless of batch size. Make them team standards, not individual habits. The full tutorial, with complete working code for every pattern covered here, including the bulkified trigger, static variable caching, the CPU checkpoint pattern, queuable deferral, batch apex, and the complete governor limit reference table, is at realsyllabus.com. If this helped, the article goes deeper on debug log reading and the combined opportunity trigger example that wires all of these patterns together.